When we drive across bridges every day, most of us barely think about them. To us, they're just roads in the air that get us from one place to another. But if you stop for a moment and look closer, bridges are far more than just concrete and steel. They are hidden masterpieces of human engineering. Constructing a building on land is already a complicated task, but building a bridge is on another level altogether. Unlike buildings, which mainly carry fixed loads that don't move, bridges face moving loads every single second. Trucks, buses, cars, and sometimes even trains pass over them. These moving loads create dynamic forces that the bridge must absorb without shaking, tilting, or cracking. A bridge doesn't just hold weight, it holds weight in motion, and that makes the challenge 10 times harder. Now imagine taking this challenge off the land and into water. Suddenly the difficulty doesn't just double, it multiplies. Because in water, engineers are not just fighting against gravity and loads, they're fighting against water pressure, waves, currents, unpredictable soil, and sometimes even tides. And here's the shocking part. In water construction, a difference as small as 1 millimeter can lead to disasters. If a foundation shifts or cracks even slightly, it can mean billions of dollars lost and, worse, thousands of lives at risk. That brings us to the foundation. Whether it's a house, a skyscraper, or a bridge, every structure stands on one thing, its foundation. And just like you can't build a tall tower on soft sand, you can't build a bridge without first creating a rock-solid foundation. But here's the question. How do you even create a foundation under tons of water? How do engineers work beneath rivers, lakes, or deep ocean waves? And how do they make sure that the foundation stays strong enough to hold a massive bridge for decades or even centuries? The process starts long before a single pile or concrete slab is laid. The first step is always investigation. Before anything else, engineers need to understand exactly what lies under the water. How deep is the water? What kind of soil or rock is at the bottom? Is the seabed made of loose sand, hard clay, or solid bedrock? All of these questions must be answered before construction can even begin. To collect this data, engineers don't just rely on guesswork. They send divers into the water to study the seabed. They use sonar scans and geotechnical tools that can push deep into the ground to measure soil resistance. Sometimes a device called a cone penetration test is used. It works by pressing a steel cone into the seabed. Sensors inside measure how much resistance the soil provides, which helps engineers understand how deep they must go to find solid ground. The water is shallow, construction is simpler. Divers can work safely, and machines can be placed on barges to assist them. But if the water is deep, like in an ocean or a wide river, the risk increases dramatically. Costs go up, timelines extend, and every step becomes slower, more dangerous, and more expensive.
Once the survey is complete, the next step begins, creating a dry place to work. No matter how deep the water is, engineers must somehow make part of it dry so they can build the foundation as if it were on land. And this is where some of the most ingenious engineering methods come into play.
The first method is the cofferdam. Think of a cofferdam as a temporary wall built inside the water. Traditionally, this wall was made of soil dumped around the construction site until it rose above water level, enclosing the area. Then water inside the circle was pumped out, leaving a dry spot where workers could start building. But the problem with soil cofferdams was that water pressure would often wash the soil away. If the soil weakened even a little, water would break through, flooding the construction site and putting workers in grave danger. So modern engineers came up with a stronger solution. Instead of soil, they used steel sheet piles. These are long, heavy sheets of steel with interlocking edges. Machines hammer them deep into the seabed, locking them together to form a watertight wall. The sheets are arranged in a circle or a square around the site. Once they're in place, water pumps remove the water inside. The workers step in, and construction begins. When the foundation is finished, the steel sheets can be pulled back out and reused for the next project. The second method is the caisson. A caisson is basically a giant box made of reinforced concrete or steel. It is closed at the bottom but open at the top. Think of it like a giant cup turned upside down in the water. Caissons are built on land first, then transported to the construction site by ships or barges. Once they're in position, engineers slowly sink them by adding weight or removing soil from inside. To prepare for this, stones and gravel are often dumped at the bottom of the water to form a stable base. When the caisson reaches the bottom, concrete is poured inside to make it heavy and stable. Over time, the caisson becomes part of the permanent foundation of the bridge. There are different kinds of caissons too. For example, open caissons have no bottom at all. They sink into the soil as material inside is dredged out.
Pneumatic caissons are pressurized inside so workers can dig while keeping water out. These methods allow engineers to build very strong, permanent foundations in relatively deep water. The third method is pile foundations. This is usually the best option when the water is too deep for cofferdams or caissons. Piles are essentially giant pipes made of steel or concrete. They can be as wide as several feet in diameter and as long as 100 feet or more. These piles are transported to the construction site and then driven deep into the seabed. But here's the challenge. A pile that big and heavy cannot just be pushed into the ground by machines. So engineers use special equipment called pile drivers. A pile driver lifts a heavy hammer, sometimes weighing several tons, and drops it repeatedly onto the pile. Each strike forces the pile deeper into the ground until it reaches solid rock or a point where the soil resistance is strong enough to hold it firmly. In some cases, instead of hammering, vibratory drivers are used, which shake the pile at high frequency, allowing it to slide into the ground more easily. Once piles are driven to the required depth, they are filled with concrete and reinforced with steel bars. When many piles are grouped together, they form a foundation strong enough to hold the weight of an entire bridge, even across wide rivers or ocean inlets. All of these methods sound straightforward when explained, but in reality, they are incredibly complex. Water pressure is always pushing against the walls. Leaks can appear at any time. Workers must constantly pump out water, reinforce weak points, and monitor for cracks. And all of this takes years of effort, massive amounts of money, and the hard work, and sometimes even the lives of construction workers. But when it works, the result is nothing short of astonishing. Some of the longest and most famous bridges in the world were built using these exact techniques. The Lake Pontchartrain Causeway in Louisiana, stretching nearly 24 miles across water, stands on thousands of piles driven deep into the lakebed. In China, the Danyang Kunshan Grand Bridge, the world's longest bridge at 102 miles, required foundations built in rivers, lakes, and wetlands using advanced caissons and piles. These structures prove what human engineering can achieve against the odds of nature. Even though the process is risky and expensive, engineers continue to perfect these methods. Modern technologies like 3D sonar mapping, automated pile drivers, and advanced concrete mixes make construction safer and stronger than ever before. Additives are used in underwater concrete to prevent it from washing out in water. Tremie pipes allow concrete to be poured directly underwater without mixing with surrounding currents. Every detail matters, because a bridge isn't just meant to last a decade, it's expected to stand strong for a century or more. So the next time you drive over a bridge, especially one crossing a wide river or the open sea, remember this. Beneath the road you're driving on lies an invisible world of engineering genius. Massive steel walls, giant concrete boxes, and piles driven hundreds of feet into the earth, all hidden underwater, working silently to hold the bridge steady against storms, waves, and time itself. So next time you glance at the water under a bridge, imagine the unseen world below, because what lies beneath is the real masterpiece.